Hello everyone, welcome to Exploring Diana YouTube series where we explore the powerful capability of Diana one step at a time. My name is Solmaz and today I will go over to explain one of our tutorials in Diana website with title Transient Dynamic Analysis of a Machine Foundation. Let me describe the problem and after that I will jump to Diana environment to start the simulation. In this video, we are going to model and analyze a concrete machine foundation that is placed on a steep over consolidated silty sand. Basically, we have got a frame type foundation with a concrete base raft and it's supporting two heavy duty compressor, one high pressure unit with a 60,000 kilograms weight and a low pressure compressor with a 40,000 kilograms weight. Both of these compressors spin really fast. We are talking about 6,000 rounds per minute, which is 100 rotations per second. That kind of a speed creates dynamic forces due to the imbalance in the machines. As you can see on the screen, the formulation for the imbalance force is presented on the screen. The M in this formulation is represent the rotating mass, E is the eccentricity, and F is the frequency of the rotation. One important design consideration here is a vertical vibration amplitude at the base of the foundation. We want to make sure that it doesn't exceed 80 microns, and that is our limit in this simulation. In this slide, as you can see on the screen, we have a table of material properties. The foundation is made of a standard C3037 concrete and using the Eurocode 2. The foundation is placed on a layer of the steep over consolidated silty sand and we are going to model the soil by using the Mohrblum material. For the compressor, we are simplifying setup the compressor machine by considering the two mass point object in the Diana. They sit on a rigid massless steel frame which help us to isolate the dynamic behavior of the system. In this model, to capture the interaction between the foundation and the soil, what we call it as a soil structure interaction or SSI, we are using a no tension stiff interface. This basically means that the soil and the foundation can push against each other but not pull apart. And yes, now I have described all required information and now we can move to Diana environment to start the simulation. This is a Diana environment. In Diana, as a first step, we need to create project. So I come to File, New, I call it Machine Foundation. In the analysis tab, I need only a structural type. It's a three-dimensional problem. And for the model side, I want to select 100 meter. And for the measure type, I will select the hexagon or quadrilateral measure type. And for the meshing order, for the sake of simplicity, I will select the linear. I press OK and come for a second and wait for a second until Diana create the project. Yes, this is a Diana project. After that, I come to unit, meter, kilogram, Newton, and for the angle, I need to change the angle to degree. All is good. So, at the second step, I need to generate geometry. For the geometry, I have three options in Diana. The first one is using the action toolbar in the right side of the window. The second one is a command console and using the Python script. And the third one is importing the model from the CAD file. In this tutorial, I need to define and assign many details to the model. So to save time, I will copy and paste the Python script to the command console to generate the geometry. Wait for a second. Very good. As you can see on the screen, we have a foundation, we have a frame, and two mass point for the equipment. After generating the geometry, I need to assign the material properties to all elements in this model. So I come to the shape properties. As a first step, I want to select all elements with the concrete material. So the element class is a structural solid, and for the material, I need to create a new material. I call it concrete. In the concrete design code, I want to select the Eurocode 2 1992. And the aspect to be included in the model, I want to select the total strain crack model. So we have some predefined the data for the Eurocode 2 for the tensile behavior and also for the compressive behavior. Very good. I come to apply. The second material that I want to define the model is related to the frame object. I select the all frame beam and the top beam frame. The element class is a class 1 beam 3D. For the material, I need to create a new material. I call it steel. In the class steel, I need to select a linear elastic isotropic. And in the linear elastic isotropic material, I need to assign the Young modulus, Poisson ratio, and mass density. Very good. And also for the geometry, I need to create a geometry. I call it pipes. Is a predefined profile. The shape is circular pipe. And I need to assign the outer diameter and thickness to this geometry. Very good. And now I will click on apply. In this model, 2-point body are being created for the high pressure compressor. And just let me show you. And the other for the low pressure compressor. We need to define the material properties for these two objects. I come to the shape properties. In the element class point mass or damping, and I need to create a new material. I call it HPC, high pressure compressor. Point mass. And in the material properties, I need to input the concentrated mass of HPC. Damping coefficient 0. Very good. I need to repeat these steps for the low pressure compressor, but I need to assign the different material properties. So I call it low pressure compressor, point mass. And in the material definition, I need to input the 40,000 kilograms for the concentrated mass for the low pressure compressor. Wait. I have one remaining item in the geometry that I need to assign the material properties to it. The last one is a soil. So again, I come to the shape properties. In the material class, I select the structural solid. For the material, I need to create the new material. I call it soil. In the soil and rock category, I select the Moore column and Drager-Prager plasticity. Okay. In this step, I need to input the material properties data to the linear material category. So, but the Young modulus 1.6E8. The Poisson ratio is 0.3. And for the mass density specification, I select the saturated density and input the data. For the Morcom and Drager-Prager plasticity, I need to input the cohesion. For the friction angle, 32 degree. For the dilatancy angle, is a 2 degree. And for the friction hardening, I select the constant friction angle. And for the tension cutoff, I select the no. The last one is the initial stress that I input the 0.47 for the K0. Very good. Now I come to apply. And as you can see on the material toolbar, we have assigned the material properties to the concrete part, steel part, soil, and also two compressor as a pointed mass object. So after generating the material and defining to all elements in the model, now I need to support the all outer face of the foundation in three directions. So I come to support. I call it support soil X. Also, I need to create a support set. And in the target type, I need to select face. In the supported face, I need to select the face which their normal is in an X direction. And then I fix the T1. The second support is support soil in Y direction. I need to create a different set for the Y direction. And in the supported face, I will select the faces which which normal is in a Y direction. And I will fix the T2. And the last one is related to support soil Z and also support set in the Z direction. And for the face, I will select the bottom face of the foundation and fix T2. Very good. Now I come to the connection and define the soil structure interface for this model. To properly simulate the interaction between the concrete foundation and the soil, we are defining an interface with a no tension behavior in the vertical. What that means is the soil and the foundation can press against each other, but they can't stick or pull away from each other. This is a key part of the modeling soil structure interface or SSI. Creating this surface is actually super straightforward. Let's me to show you. So I come to the connection. I call it SSI, soil, the abbreviation for the soil structure interaction. The type is interface. Mode is closed. And for the source face, I need to select the bottom face of the floor. And for the target face, just let me show only the foundation. And for the target face, I need to select the upper face of the soil. For the element class, I need to select the structural plane interface. And for the material, I call it SSI, the element interface class. For the material model, I need to select the nonlinear elasticity. Very good. So the type is a tree surface interface. For the normal, I input the normal stiffness modulus in the Z direction. Also, I need to input the shear stiffness in the X and Y direction. For the nonlinearity, I select the no tension with a constant shear stiffness. Very good. And for the geometry, I need to add the new geometry. I call it again SSI. And for the local element axis, the local x-axis is in x, global x direction. Very good. I come to create. Now I have the interface between the soil and also the top floor slab. Let me show you the whole model. The interface between the soil and the floor slab is illustrated by the blue dot on the soil and red dot on the bottom face of the floor slab. So in the connection toolbar, we have a soil structure interface in this model. Since we are not adding any damping to the concrete or the soil in this model, we need to make sure that waves generated by the rotating machinery don't reflect back from the edges of the soil block. So to deal with that, we are using perfectly matched layer or PML boundary condition. These are special layers designed to absorb the outgoing wave and they don't reflect into the domain. In this setup, we are using two PML zones. The first PML layer sits right at the same level as the soil block and is designed to absorb wave traveling horizontally. The second PML layer is placed below both the soil block and the first PML zone, and this one handles waves traveling in both horizontal and vertical direction. In this step, I need to create the two PML zone. So I come to the block, I call it PML 1, and for the position is I need to input data minus 21.1, minus 19, minus 10, and for the size I need to input data regarding the block, PML block 1. Very good. And close the window. I need to subtract the soil from the PML zone 1. For this purpose, I come to the subtract. For the target, I use the PML 1. For the tools, I will select the soil 1, soil, and I need to keep the tools. Very good. So the second step is creating the PML layer 2. So again, I come to the block. I call it PML, 2. And I need to input the position and also the size. Minus 21.1, minus 19, minus 20. And for the size, 43, 38, 10. Now we have a 2 PML block in this model, and to complete the setup for the perfectly matched layer, we need to define the function in all three global directions. These functions should have a value of 0 where they connected to the soil, since there is no damping in the soil. On the other side of the PML at the boundary that will be supported later, these functions should be equal to 1. The damping of the waves only happens in the regions where these functions have a non-zero value, so they essentially control where and how the waves are absorbed as they travel through the PML zone. For this purpose, I need to assign a three function to the model. I come to the geometry function add. The first one I call it PML X. And for the data, I copy and paste data from Excel to the Diana very quickly. Very good. Again, I come to the geometry function. For the second function, PML Y. In the function parameter, I select the Y. And for the data, I copy and paste data from Excel to the model very easily. Very good. And for the last one, I call it PML, PML Z. In the parameter function, I select the Z. And for the data, again, I use the data from the Excel file and copy to the diagram. Very good. Now I have the three function in three global direction, X, Y, and Z. After defining the function, I come to the shape properties and select the PML1. The element class is structure solid. For the material, I call it PML1. In the soil and rock, I need to select the perfectly matched layer. Very good. I need to input the linear material properties and also perfectly matched layer properties. For the linear material properties, I input the data for the Young modulus, Poisson ratio, and mass density. For the perfectly matched layer, for the layer 1, I select the defined PML parameter in the X and Y direction. For the function, for the X direction, I need to select the PML X, and for the Y direction, I need to select the PML Y. Very good. You can choose to see which function is assigned to your model. I will click on apply. Again, I will select the PML2. The element class is a structural solid. For the material, I need to create the new material properties. I call it PML2. In the soil and rock, I come to the perfectly matched layer material model. And again, I need to input data for the linear material properties. For the Young modulus, Poisson ratio, and also mass density. And after that, I need to set up the PM perfectly matched layer properties. In this zone, I mean the PML layer 2, I need to have a PML parameter in all three global direction. For the X direction, I will select the function for the X. For the Y direction, I will select the function in Y direction. And also for the last one, I will select the PML Z. Very good. Now I have assigned the material properties to all elements in the model. The last step in this part is supporting the outer face of the PML zone. So I come to support. I call it a PML support PML X I need to add a support set. And for the face, I need to select the face which their normal is in X direction. And I fix the T1. The second support is related to support PML Y. Also, I need to add a support set for the Y direction. And again, I need to select the faces which their normal is in Y direction. And I fix the T2. The last one is related to bottom face of the PML layer. I come to support again. I call it PML, support PML Z. Again, I need to create a support set. And I select the bottom face of the PML layer and fix the T3. Very good. Now we have assigned all material properties and support to the PML. So now it's time to assign the load to the model. For the stress initialization in the soil, a deadweight load has to be defined in the model. So for this purpose, I come to the global load. I call it SW, the abbreviation for the self-weight. I need to add the load case. I call it SW, and the load type is a dead. To simulate the forces caused by the unbalanced rotation of the compressor, we are defining 4 separate load cases. Each one represents a different phase of the rotation. For each load case, we attach a time factor curve that captures how the direction of the force changes over time as the machinery spins in the model. For this purpose, I need to define the load for the low pressure compressor and the high pressure compressor. Let's start with the low pressure compressor. I call it LPC. The name is a torque. LPC for the low pressure compressor and in a Y direction. I need to add the load case. The load target is a vertex. The load type is a force. And for the loaded vertex, I need to select the LPC. The force value is a 1 and the direction is a Y. Great. The next one, we need to apply the unit load in the global Z direction. So I call it torque LPC in a Z direction. I need to add the load set for the Z direction. Again, for the targeted vertex, I select the vertex of the LPC and the direction is a. We need to repeat these steps for the high pressure compressor or HPC. So I call it torque HPC in Y direction. I need to add the load set. And for the loaded vertex, I select the HPC and the direction is a Y. The last one is torque HPC in a Z direction. Again, I need to add the load set for this load case. And for the loaded vertex, I select the vertex of a HPC. And the direction is a Z. Very good. Now I come to the load toolbar. As you can see, we have a self-weight and the 4 different load cases. to simulate the different phase of the rotation. So in this step, we need to assign the time-dependent factor to the all torque load cases. The forces in the y and z direction are a function of the time, and as you can see on the screen, we have a two equation for the low pressure compressor and high pressure compressor. In this formulation, A represents the unbalanced force, amplitude of the unbalanced force, and F represents the rotation frequency. So let's start with the torque load for the high pressure compressor in a y direction. I come to the time dependency factor and copy and paste data from Excel to the model. So I come to the HPC in a Z direction and only copy and paste data from Excel to the model. I need to repeat this step for the all four load cases and copy data from the Excel to Diana. Very good. And the last one is low pressure compressor in a Z direction. Very good. Now we have assigned the four time dependent factor to the four load cases which is related to the unbalanced force in this model. Now we are one step behind the analysis setup. In this model, we want to have a different element size for the different object. So I come to the mesh properties. I select the element size for the seeding method, and I select the different element in this model. Very good. And for the desired size, I want to consider the 0.5 meter. Apply. For the soil, I want to have a different the seeding size. I consider the 2 meter. And for the PML1 and PML2, I want to consider the 4 meter for the seeding size. Very good. Now I need to generate mesh. Just wait for a second until Diana create a very beautiful mesh to the model. In this step, we need to define the analysis setup. But for sake of saving time, I prepared the one model before to show you how we need to arrange the analysis setup, and after that I will show you the result. As you can see on the screen, first we run the eigenvalue analysis to check the model's natural frequency. Let me show you the phase. In this phase, the PML boundaries are turned off to avoid interfering with the result. After the eigenvalue analysis, we move to the transient dynamic with the three different phases. In the phase 1, we initialize the soil stresses and using only the soil dead weight. So no machinery or foundation is active yet. In the phase 2, we install the machine foundation and active the soil and structure interfaces. Still no dynamic loading or PML at this stage, as you can see on the screen. And in the phase 3, this is a dynamic analysis. All parts, including the PML, are now active. The unbalanced forces from the rotating compressor are applied to the model. And so let me show you some part of the result. For example, the first result that I want to show you is related to the eigenvalue. Here we can have a eigenfrequencies for the system. I come to the result, select the total displacement in the X, Y, and Z. And now we will have a eigenfrequencies for the foundation and the structure. Very good. The second result that I want to show you is related to the second analysis, I mean the transient dynamic analysis. In the phase one, I want to show you the stress, the total Cauchy total stresses in X, Y, and Z direction. This result is related to the soil stress initialization in the soil, and you can see the layered cake in the soil in this model. In the final step, I want to check the displacement in the perfectly matched layer to ensure that they are effectively absorbing vibration. Since this tutorial is using a coarse mesh, it's recommended to have at least 5 elements across the PML region for the better accuracy. Based on this recommendation, I have changed the meshing of the PML region to the 2-meter element size. And let me show you the second model that I have changed the meshing for the PML region. And let me show you the result regarding the displacement in the perfectly matched layer. I come to the transient analysis, and also in the last step, let me select the displacement, total displacement in the X, Y, Z, and just only let me activate the PML part. As you can see, the value for the total displacement, the X, Y, Z, is very small. I also want to monitor the dynamic displacement at the four corner of the slab. At the four corner of the floor slab for the all-time step to ensure that the maximum vertical amplitude stay below the 80 microns. For this purpose, let me select one of the corner points on the floor slab, and after that I come to the displacement, for example in the Z direction, show table, and I want to select a time step. As you can see on the screen, the response is located in the acceptable margin for the rotating machinery. And also, I want to show you how the PML or perfectly matched layer works. Let me select a point on the PML region. Just first of all, I want to show you only the PML region. Yes, that's it. For example, one point here. And if I come to the result, show table, time step, and as you can see, as we move toward the outer boundary of this condition, I mean, I'm coming out to the region of the PML, the displacement is gradually decreased and indicating that the boundary condition is functionally effective in this model. At this point, the simulation is over, and now I want to show you how you can find this tutorial on Diana website. Just let me open Diana website. Under the Get Started category, you can come to the tutorials. And in tutorials page, based on the tutorial type, analysis type, and model required, you can define your preferred tutorial. For example, here I want to select the technical dynamic type. And also for the analysis type, I will select the structural nonlinear. And yeah, that's it. And you can find the transient dynamic analysis of the machine foundation tutorial on Diana website very easily. Thank you for your attention. Please don't forget to subscribe the Diana YouTube channel.